Hi everyone. So in the last module, I have completed introduction to reinforcement learning. So there I discussed like what is reinforcement learning, what are the application and what are the algorithms used in reinforcement learning, and also I showed you a snake game where I have shown that how reinforcement learning is being used in that game. So this is the starting of a new module. So in this module we will discuss about like exploration and exploitation in multi-armed bandit. So 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 the like I some of the slides I have taken from like Reach Sutton's class, and you can follow the book Introduction to Reinforcement Learning by Sutton, and this is a great book, and you can refer to that book. Yeah. So what is supervised learning? Like in the previous module I have discussed, like supervised learning is like instructive feedback. So the expert directly suggests correct action. So we know that in supervised learning we have a data set, we have the data and the label, and uh, and then learning by interaction, like this evaluation feedback. So reinforcement learning is, in the reinforcement learning we have an environment. The environment provides a signal whether the actions the agent selects are good or bad, and not even far away from the optimal actions. And evaluation feedback depends on the current policy the agent has. So we all know about the, if you can remember, like in the reinforcement learning, we have our environment, we have an agent. The agent takes an action and gets some reward from the environment. So this is the overall like theme of reinforcement learning. And the exploration means like active search for good actions to execute. So so sometimes we have some dilemma between exploration and exploitation. So you need to know the basic difference between exploration and exploitation. So suppose online decision making involves a fundamental choice. So exploitation means like make the best decision given current situation, and exploration means like gather more information. So sometimes the best long-term strategy may involve short-term sacrifices, and gather more information to make the best overall decisions. So this is the exploration, to gather more information. So there are some example, like real life example, to be able to understand the difference between like exploration and exploitation. Suppose you went to a new city and you want to like explore the restaurants in that city. So in case of restaurant selection, sometimes you want to go to your like favorite restaurant. So you may heard some from someone like, so this restaurant is best. So you directly go to that favorite restaurants, or sometimes you try to explore new restaurants. So this is exploration. So exploration is trying a new restaurant, and exploitation means like go to your favorite restaurant. Then suppose drilling, in case of drilling, so you want to drill like best known location. So this is exploitation, and exploration is like drill at new location. Similarly, like for game playing, you want to play the move you believe is best. So this is exploitation. You already know. Okay, so I should take this move. And the exploration means like play an experimental move. Okay, so this is the like basic difference between exploration and the exploitation. So this is like I like talked about this figure like multiple times. So here we can see like we have an agent. So the brain, this is like agent, and this is the environment. So agent takes some action, and this action leads to some new state. So here st plus 1 denotes the state at time state, like next time step, and get some reward like rt plus 1. So initially we have a state and reward. So agent, by taking this state and reward, agent takes an action, and then it goes to new state and new reward. So here we can see like so agent and environment interact at discrete time steps. So here t denotes time steps. Agent observes state at step t. So st belongs to number of states. So this is the like it belongs to s. So s is a set of states. This capital S, and produces action at step t, and action at step t belongs to some set of actions, gets resulting reward like rt plus 1 belongs to r, and the resulting next state is st plus 1. So here we can see like this is a diagram. Like initially we have a step, we take a action, then we move to next step, and there we get some new reward. So this is the like overall concept of like reinforcement learning. So now what is like multi-armed bandit? So basically multi-armed bandit problem can be effectively like applied in many scenario. So we will discuss more about what is multi-armed bandit. So you can see like, so this is some like in casino. So there are some game. So there is a like arm. So you pull the arm and you get some reward. So this is the basically multi-armed bandit problem. So this is like one armed bandit. So this is the pull arm. So when you pull arm, you get like some rewards here, and then you can like eventually win or lose. So I have a question for you. So tell me, what can be the states and actions in this in this one-armed bandit problem? Just think and just tell me. Okay. So this is like the multi-armed bandit problem. So here we can see like there are multiple arms. Like in that figure, you can see there are like multiple arms, and these are my action. So suppose there are like 1 to n arms, and this action is a set of like, so a is a set of actions. So you can pull 1, pull 2, and then you get some reward. So so reward is like, so reward at action n is the probability of reward given action. Like we don't know like what are the reward distribution, but there are some probability. So this is the like multi-armed bandit problem. So there we have multiple slot machines. So multi-armed bandit problem, like at each time step t. So at each time step t, the agent chooses one of the k arms. So let we have a k arms and plays it, and the ith arm produces the reward it when played at the time step t. So the reward are drawn from a probability distribution of pi with mean mu I. So we have some probability distribution of rewards, and the agent does not know neither the arm reward distribution or neither their means. Like the agent don't know anything, but it will. So when I don't know anything, so I will do like either exploration or exploitation. So the notation for the mean arm reward is like q star. So q star is like optimal rewards. So this is the expected value. Like this, the expectation value means like mean. So mean of all rewards given action, given all the action. So for each action we have a reward, and expected value of the rewards is the mean value of all the rewards. So this is the notation. So E for like expectation, like mean value. So this is reward RT given the action T, and A is a set of like K arms. So we here you can see like we have the K arms. So what is the agent's objective? So in reinforcement learning, so we already said that we have a environment, we have an agent, and we want to maximize reward. So the agent's objective is to like maximize cumulative rewards. So in other words, we should say like find the arm with the highest mean reward. So this is basically a multi-armed bandit problem. So there are some like concept based on Bernoulli's bandit. So I think some of you already know like what is Bernoulli bandit problem. So Bernoulli distribution. So if you have taken classes of probability, so there you know like what is like Bernoulli distribution. So Bernoulli bandits are a specific type of multi-armed problem where each arm provides a reward according to the Bernoulli distribution. So in Bernoulli distribution, each arm has a fixed but known probability of yielding a reward 1 or 0. Like so, if you here can see the like definition, the Bernoulli distribution is a discrete probability distribution of a random variable which takes the value 1 with probability p and the 0 with probability q, which is 1 minus p. That is the probability distribution of any single experiment. So that asks a yes no question. So this is the Bernoulli distribution. So in Bernoulli probability distribution, we have a reward which is 1 or 0, that is binary. And each action, so here action means pulling the arm. So in like slot in the slot machine there is an arm, so action means pulling the arm. So each action results in a success or failure, like it. So rewards are binary, and the mean reward for each arm represent the probability of success, and the action k belongs to 1 to k produces a success with probability that belongs to 0 and 1. So here you can see like so just think, so what should be the objective of Bernoulli bandits? So what is objective of reinforcement learning? If you can recall, like in the first module I have said that what is the objective of reinforcement learning? So the objective is to like maximize the rewards. So in case of like Bernoulli bandits, the objective the objective is to maximize the cumulative rewards over a series of arm pulls. So this involves identifying the arms with the highest probability of success and pulling it most frequently. So now I think like you got it, like what is the like objective of Bernoulli bandits. So if I ask you what should be the like exploration versus exploitation in case of this bandit problem, just think. So exploitation means like choosing the best term, and exploration means like exploring different arms. So the agent must balance between exploration, like trying different arms to gather information about their probabilities, and exploitation, that is pulling the arm with the highest estimated probability of success. So here you can see, so if you this is some distribution, like reward distribution. So we call it like Gaussian distribution. So here Q star denotes the like optimal like action, that is like optimal like action for getting the best reward. So here action means pulling the arms. So here, like in x-axis, these are my actions, and for different actions, we have like different reward distribution, and these are the like Q star, that is optimal action to get the reward. So now we will talk about like where this multi-armed bandit problem is used in real world, like some real world motivation. So the multi-armed bandit problem can be effectively be applied to optimize the images displayed for a particular movie on Netflix to maximize the user engagement. So I'm telling again, like to optimize the images displayed for a particular movie on a Netflix to maximize the user engagement. So the problem setup is like this, like choosing one of the k different images to display for a particular movie on a user's home screen. So when you open Netflix for different movies, you get like some different images of the movie, and so your objective is to like show the user such kind of image so that the user click on that movie image to see the movie. So here action is like choosing one of k images to display for a particular movie on a user's home screen, and the ground truth mean rewards, which is obviously unknown, the true percentage of Netflix users that will click on the movie title and watch the movie for each images. So this is my ground truth. And then we want to estimate the mean rewards, the observed average click rate for each image representing that quality like management. So I hope like you understand the problem. So if this is the problem. This problem name is called like Netflix artwork. So if you search on Google, so you will know more about like what is Netflix artwork. So 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 applying multi-arm bandits to Netflix artwork. So if you want to try to define the arms, so what should be the arms? So each arm in the bandit problem correspond to one of the k images available for a movie. So here you can think like arm as the images that is available for a particular movie, and the reward is the for like reward for pulling an arm. That means displaying an image is binary. Suppose so if the user clicks on the movie after seeing the image, 0. If they do not so if the user clicks on the movie after seeing the image is 1, and if they don't click the image, so it is 0. So just think, so then what should be the objective? The objective is to like maximize the cumulative rewards over time by identifying and displaying the most effective image. So okay, so what is cumulative reward? So what should be the reward here? Just think. So the reward is like the total number of clicks. So suppose you form some estimates. So this is like action values test estimates. So this is my like optimal action, and this is the set of actions. And so uh, now define some greedy action at time step t as like, so if you so what should be the like best action? So if you take the arg max of the qt, so qt is the like available actions. So if you choose the best action, that means you are exploiting. So you just directly choose the best action. And if you don't choose the best action, that is at is not equal to a star t. So here a star means optimal action. So here like optimal means like best action. So you can't do both, but you sometimes need to do both. But in reality, you can't do both. So now we will, so until now, so we know that what is multi-armed bandit problem. And also I give you some like description of multi-armed bandit problem in Netflix, like artwork problem. So now we will know about regret. So just think like, what do you mean by regret? So regret is a like key concept in the study of multi-armed bandit problems and the reinforcement learning. So it measures the difference between the rewards. Just listen carefully. So the rewards measures the difference between the regret measures the difference between the rewards that could have been obtained by always selecting the optimal action and the reward actually obtained by the agent over a series of decisions. So here you can see like Q star. So Q star is like best like expected return given all the actions. So this is the mean value, like mean value, and the optimal reward is like maximum of this Q star A. So the regret is the opportunity loss for one step, like it's the difference between the best action and the chosen action. So regret basically quantifies the performance loss due to not knowing the optimal action from the start and having to explore and learn over time. So the total regret is, this is the regret for one time step. So the total regret is like summation of all time step. So this is the like best reward minus Q star reward, like chosen reward. So this is my total regret. So the count NT is like the number of times the action A has been selected prior to time T. So this is the count. So count means the number of times that action A has been selected prior of time T. And the gap is the like difference in between action A and the optimal action A star. And the regret is the function of the gaps and the counts. So here you can see. So this is the like a action, and this is my optimal action. So this is my the function of like gaps and the count. So count is the number of time the action has been selected. So this is regret. So now we will learn about forming action value estimates. So what is forming action value estimates? Here you can see. So we consider only its reward after its estimate after n plus 1 rewards. So here un equal to Rn plus 1, un equal to, so 1 minute I just, so qn equal to R1 plus R2 plus Rn minus 1 divided by n minus 1. So we only consider its reward and its estimate after n plus 1 rewards. So now think, how can we do this incrementally, like without storing all the rewards? So we can take the running sum and count equivalently. So q n plus 1. So what is q? So q is like action values function that represent the estimated value of taking action A. So qa means, so the formula of qn plus 1. So this is like qn plus 1 by n Rn minus Qn. So like we can derive it using some incremental update rule formula. So we will like see. So the standard form of for learning or update rule is like like new estimate equal to old estimate plus step size into target minus old estimate. So just take some note, like what is incremental update rule. So incremental update rule, like a method to update the action value incrementally as new rewards are observed. So this is my incremental update rule. So if you see, so this is my like derivation. So what is, so Qn equal to R1 plus R2 plus Rn minus 1 divided by n minus 1. So what is Qn? So Qn is the current estimate of action, like current estimate of action value after n observation. And what is like Rn, like Rn, so Rn means like observed reward. And what is n? N is the count of observation. So the Qn is like, so Qn plus 1 equal to 1 by n and the summation of all the rewards in all. So n is the observation and summation of all the rewards in each observation. And then you take the last reward like Rn, and you here you just take the like n minus 1, like simple math. And then here you can use like n minus 1 into 1 minus n minus 1, so it will be like cut down. And this value like 1 n minus 1, and for I equal to 1 to n minus 1 Ri equal to Qn. So this is some kind of following some recursive property. And then your Rn equal to nqn minus qn, and if you just simplify this, so you will get Qn equal to Qn plus 1 equal to Qn plus 1 by n Rn minus Qn. So okay, so what do you get from this derivation? Just think. So the derivation like clearly shows like how current estimate is adjusted based on the new observation. So now we will learn about new thing like non-stationary bandits. So in a non-stationary bandit problem, the true action values changes over time. This means like the probability of receiving a reward from a given action, so here action you can say like arm, is not fixed and can be very slowly or abruptly during the decision making process. So basically like non-stationary environment are really common in real world applications such as like financial market, like adding placement. So ad placement, like sometimes we just Google shows us some ads. So these ads are like non-stationary. The optimal action can change over like time. So why like sample average? So in the reward we are taking like sample average. So why the sample average are not a good idea in non-stationary bandits? So the sample average, like stationary environment, in a stationary environment the true action values are constant, and the sample average of received rewards from an action provides an unbiased estimate of true action value. But in case of non-stationary, so the sample average gives the equal weight to all the past observation. This means the old information which may no longer be relevant has the same influence on the like estimated action value as recent information. So the simple takeaway from this slide is like simple average are not a good idea in case of non-stationary bandits. So suppose, so I told this earlier, like simple average is not a good idea in case of non uh, stationary bandits. So what is the solution? So to address the challenges posed by the non-stationary environment, a more effective approach is to use an exponential recency weighted average, and the method gives us more weight to recent rewards, allowing the estimated action value to adapt more quickly to changes. So this is called exponential recency weighted average. So so here you can see the formula like un plus equal to qn plus alpha rn minus qn. So just take a break and see, tell me what is qn plus 1 here. I hope you pause the video and just think. So what is qn plus 1? So qn plus 1 is the updated action value estimate after the n plus month trial. And and ri denotes like rewards. And what is alpha here? What is alpha here? So alpha basically is a constant between 0 and 1. That it's a 0 and constant between 0 and 1 that determines how quickly the estimate adapts to a new observation. The smaller the I, the smaller the like multiplier. So this is like in case of non-stationary bandits. Thank you.